Okay, I want to go now over the Jupyter notebook to train a deep perceptron or a one-layer perceptron uh, to model the XOR gate. Okay, why we need the linear the deep perceptron? Because if we go back to our Python code to model to train a linear perceptron to for Boolean gates, for example, no, in this code, this is the linear perceptron. If we want to train a XOR gate, I changed the data. I already prepared them. And you know, we already have seen this code, so it's gonna go through a training of the weights and bias, and then it does a testing of the perceptron and some plotting. So let's see what happens if when we try to train a XOR gate, run it. You see that the error basically doesn't go to zero, and we get to a constant non-zero value. And when we test the trained perceptron with this with the converged weights and bias, you see that there is no much. So the predicted output does not match the data for these two values here. And why? Because when we plot the data in the input space, you see that there is no way to draw a line which is able to separate the blue points from the red points. For doing so, we will need two decision boundaries, okay? So with a linear perceptron, you cannot model the XOR gate. And that's why, we need the deep perceptron. We need a multi-layer perceptron, as I described it in my lectures. And in this case, you see, I'm using a sigmoid activation function and its derivative that we needed. So in this case, the XOR data, just to change a little bit, instead of doing -1 and 1, I'm doing 0 and 1. It's the same things. And these are basically, the data point for the XOR gate. So the input data and the corresponding labels or output. And what happened here now, we have 3 perceptrons that we need to train. These two, they form one layer. And then this is basically, the final output. The one that gives the output. And again, here, we define a learning rate, 10,000 epochs. And here there is all the training loop that goes through the epochs. And then it loops over all the data points. These are basically, the input data and the corresponding target or output. And so what it does first? It first compute the first layer outputs of the two perceptron, which you see they have the same input, and they provide the Z1 and Z2 outputs. And this output become the input of another perceptron, which is modeled with both with the sigmoid, which finally give you the predicted output. And here we use least square to make sure that the target output and the predicted output are as small as possible and tending to 0. You see here the total error, it is summing up and squared. And in order to do the update of the weights, now we will need to compute the gradients of derivative of this of the error with respect to these parameters. And to do that, this is done through the backpropagation algorithm that is very efficient and is, this is basically the algorithm which you can see that does the updates of the weights. And this is repeated over all the epochs. And then what we do, we plot the loss function or training error as a function of the epochs. And then we plot the data in the input space, x1 and x2, and we also plot the data in the latent space, which is basically the output z1 and z2 of the first of the one layer of perceptrons, and also the correspondent decision boundary. Okay, and then we also test the train model. Let's run it. Let's see what we get. So we get just 3 plots. You see the training error goes down very fast, but I mean, you need at least 2000 iteration, 2000 epochs, to somehow get to a very small training error. And before commenting on these 2 plots, let's look at the testing. You see the expected output match the predicted output match the expected output for all the 4 data points. So I mean, with the multi-layer perceptron or deep perceptron, we can nicely model the XOR operator, the XOR gate. But why? Geometrically, the answer is basically in this plot. This is basically the input space, which we already have seen it, and you see that the points are separated. The blue and red point are separated. That there is no way to draw just one line to classify, to do a binary classification between blue and red points. However, this input, it is fed. It becomes the input of 2 perceptrons, which they form a layer, and they give two outputs, z1 and z2, which are hidden. They are the latent variables, which form another space. And as you can see, the 2 red points, they are mapped into the same point in the latent space. Instead, this point goes here and the blue one goes here. So now you can see that in the latent space, we can use a linear perceptron to classify the red points from the blue points using just one decision line. And that's what the third perceptron does. And that's why, we can basically model a XOR gate with a deep perceptron or a multi-layer perceptron. Because the presence, we have this latent space, which is basically, it is the latent space, latent variable, learn the outcome, the output of the first layer of 2 perceptrons. Okay? Okay, thank you.